So yesterday you got you basically started chapter 2's information. And really chapter 2 can be broken down into two key pieces. The first piece is the discoveries that led us to better understand the electronic structure. And the second piece is the mathematical computations that lead us to predict the electronic structure. So the story all begins with the electron, because like I said yesterday in labs, at the end or in the chapter previously, we talked about the subatomic particle. The proton is responsible for the element's identity. We look at the periodic table, we can determine the number of protons. The neutrons are responsible for the element's isotopes. The isotopes play directly into determining the average atomic mass that's seen on the periodic table. The electrons are responsible for the element's reactivity. And so if we're going to better understand how elements behave, we have to understand their electronic structure. Now, there is evidence that electrons can behave as light, as we saw yesterday. And there is evidence that they can behave as particles. It's called the wave-particle duality. What we're going to do is we're going to begin by talking about light, and then we'll move into the particle concept before we get into the electronic structure. Whoops, wrong thing. Okay, so there are three things that are used to describe wave. The first thing that is used to describe a wave is the amplitude. The amplitude is the height of the wave. Now, the amplitude is thought to be the result, or is thought to be the intensity. So the larger the amplitude, the more intense the light is. So you can think of a flashlight with brand new batteries. It shines very bright. It has a large amplitude. And you can think about a flashlight whose batteries are almost dead, that are just barely shining. That would have a low amplitude. So in other words, the amplitude is directly related to the intensity of the light. The second characteristic is the distance between two adjacent peaks, the distance between two adjacent troughs. Basically, it's the distance between the same point on two adjacent waves. This is the wavelength. The wavelength is represented by the Greek letter lambda. Now, it is a length, and what is the most common unit for measuring length? Meters, centimeters. So wavelengths tend to be measured in meters, or as we discussed yesterday when you were looking at the hydrogen lamp, in nanometers. The third thing that is used to describe a wave is known as the frequency. The frequency describes how many waves pass a given point in a second. So the frequency represented with the Greek letter nu has the unit of per second or waves per second, essentially. So when we see the unit, we'll see it listed as second to the -1. That means that the seconds is in the denominator. This is also referred to as hertz. So these are the three things that are the three pieces of information that can be used to describe a wave: the amplitude, the wavelength, and the frequency. Now, if you look carefully at this diagram, the high frequency wave, meaning there's lots of waves that occur per second, has a short wavelength. Whereas the low frequency wave, which means few waves pass a given point in a second, has a long wavelength. Therefore, wavelengths and frequency are inversely proportional to one another. If one is long, the other is short or low. If you have a long wavelength, you have a low frequency. They're inversely related. This relationship between the wavelength and frequency is expressed using the speed of light equation, where the speed of light is equal to the wavelength times the frequency. The speed of light in a vacuum is a constant. It is always 3.00 times 10 to the 8 meters per second. Now, that's really dependent upon which table you look at, because some tables will list it as 2.998 times 10 to the 8 meters per second. But basically, it is 3 times 10 to the 8 meters per second. Now, the speed of light, since it is a constant, dictates the units that your frequency and wavelength must be in. According to the speed of light, the wavelength must be in meters in order to use this equation. And the frequency must be in per seconds to use this equation. So again, the speed of light dictates the units. The most common mistake made is not paying attention to units. If you simply use the numbers, there's a good chance that you will make a mistake. You have to pay attention to your units. And again, the speed of light is the dictator of those units. Let's see an example. Calculate the wavelength in nanometers of red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14 per second. So what we know is we know the frequency is 4.62 times 10 to the 14 per second. We have been asked to calculate the wavelength. These two values are related to one another through the speed of light equation, where the speed of light is equal to the frequency times the wavelength. The speed of light is a constant. It is 3.00 times 10 to the 8 meters per second. So using that information, we can plug these details into the equation, and we get 3.00 times 10 to the 8 meters per second is equal to the wavelength times 4.62 times 10 to the 14 per second. Completing this calculation, you get a value of 6.49 times 10 to the minus 7, and that unit is in meters. We know that unit is in meters because the speed of light dictated what that unit must be. But always pay attention to the question. The question asked for that wavelength in nanometers. So you're going to have to take that 6.49 times 10 to the negative 7 meters, and you're going to have to convert that into nanometers, with the fact that 1 times 10 to the minus 9 meters is equal to 1 nanometer. So in other words, it comes out to be 649 nanometers. This speed of light equations and energy equations are common areas where you're going to need to be able to convert between meters and nanometers. So in other words, you're going to have to use your metric prefix conversions. Questions? Okay, so in the previous example, I gave you red light. Red light is part of the visible spectrum. The visible spectrum makes up a very tiny fraction of the overall electromagnetic spectrum. The electromagnetic spectrum starts out with gamma rays. So when I think of gamma rays, I think of the Incredible Hulk. You will notice that the frequency of the gamma rays is very frequent. The next thing in line are X-rays. With X-rays, I mean, doctors will only allow you to get so many X-rays in a year because X-rays damage cells. If we're looking at the frequency, you will notice that it still has a fairly frequent wave pattern. Then we move into ultraviolet, and there's ultraviolet A, B, and C. We know when we go out in the sun that we are supposed to put on sunscreen or something of that nature. That is because the ozone level or the ozone layer does a good job of removing the most harmful of the ultraviolet rays, but it doesn't remove all of the ultraviolet rays. And those ultraviolet rays, again, have a high enough frequency that they can cause damage to cells. Finally, we get into the visible spectrum, and then we move into the infrared radiation. Infrared, every time I think of infrared, I'm thinking of those ghost hunters. looking for the the heat signature. Infrared radiation has a longer wavelength and a lower frequency. Infrared radiation can cause molecules to vibrate, but it can't cause molecules to break. It can't cause damage. Then we move into microwaves, and you'll see the microwaves again, they have a much longer wavelength, therefore a lower frequency. Microwaves, the way a microwave works is it basically takes water and heats up the water so that it moves quickly. And it is the friction of the water rubbing against the food that causes the food to heat up. But again, it can't cause cellular damage. And then we get into radio waves. Now, so what we know is bad radiation, short wavelength, high frequency. Bad radiation is short wavelength, high frequency. That's the radiation that can cause damage to cells. That's the radiation that can cause molecules to break. The bad radiation is going to have a high frequency and short wavelength. Basically, when we're talking about that bad radiation, the reason it's so bad is because of its energy. The energy associated with that photon of light of radiation is equal to Planck's constant times the frequency. The energy and the frequency are directly related to one another. The higher the frequency, the higher the energy. They're directly proportional to one another. Now we can use our speed of light equation and substitute in that speed of light equation, and we can find out the relationship between energy and wavelength. And what you will see is that energy and wavelength are inversely related to one another. The longer the wavelength, the lower the energy. Now, Planck's constant, again, is a constant, and constants are always dictators of units. Planck's constant says that energy will be in joules. Planck's constant says that the time will be in seconds. The speed of light constant says that the wavelength must be in meters. So again, you have two dictators of units, and you have to pay attention to your units. Yes.
The videos, like the classroom videos, I saw where the 3.0 times 10 to the 8 meters per second. One time it said 3, now it's saying 3.0. Do you care how many decimals that?
Okay, so again, it all depends upon which table you look at, because you can even look at a table and it'll say 2.998. So no, I can't. I will give you a constant on the test, on the formula sheet. And so you can use that constant. But it does not matter whether it's 3 or 3.0 or 3.00 or 2.998. They'll all come out very similar in the end run. Yes.
For H, the units, is that J1?
J times S, yes. Joules seconds. So joules times seconds. Let's look at an example. Calculate the energy of a photon. Calculate the energy of a photon of light with a frequency of 15.77 times 10 to the 17th hertz. Okay, so what I have is I have the frequency. That is 15.77 times 10 to the 17 hertz. And I have been asked to calculate the energy. If we look back at the previous slide, the equation that we're going to want is energy is equal to Planck's constant times the frequency. We use that particular variation of this equation because we were given the frequency. Now, Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. So our energy is going to equal 6.626 times 10 to the minus 34 joules times seconds times 15.77 times 10 to the 17 hertz, which is per second. So therefore the energy is (1.04 times 10 to the minus 15 joules. If I'm recording this to the correct number of significant digits, I would record it as 1.045 times 10 to the negative 15 joules. Questions? Folks, the hardest part of what we've discussed so far is knowing which equation to use when. Otherwise, these equations, you are pretty much putting your study. You got to know what equation you need to use when you need to use it. When do I use C is equal to lambda times nu? Well, when I have the wavelength and I want the frequency, or I have the frequency and I want the wavelength. That's my relationship I go to. When do I use E equals H times the frequency? Well, when I have the frequency and want energy, or when I have energy and want the frequency. So one of the hardest parts is just being able to take the word problem and remember what variable goes with what piece of information. The other part is remembering to pay attention to units. And yes, I'm preaching that because units are being dictated in these problems. I would use this equation if I were given the wavelength and wanted energy. So it is dependent on what I want. So yesterday, when you were in lab, one of the pages that you had to do some calculations on required you to calculate the energy of the atomic emissions from that hydrogen lamp. Well, when you looked into that atomic emission, that spectroscope, you saw wavelengths. You were seeing wavelength. Because you were seeing wavelength when you were doing the atomic emission spectra, that is why you have to use this equation. Because I was wanting the energy and I had wavelengths. Now, the big deal about using this equation is, again, you had to make your units match. So the first thing you had to do in that calculation was convert those nanometers into meters. So I gave you 410 nanometers as the first one, for example. Step number 1 would be to take that 410 nanometers and convert that into meters. So then I would get, so it would be 4.10 times 10 to the minus 7 meters. That was step number 1 for yesterday's lab for the energy calculation. And yes, you have to do that for all 4 wavelengths. Step number 2 was to use this equation to calculate the energy. So you would have had energy is equal to 6.626 times 10 to the minus 34 joule seconds times 3 times 10 to the 8 meters per second divided by your 4.10 times 10 to the minus 7 meters. And you would do that calculation and get your energy. Again, you would repeat the process for all 4 or for the other 3 wavelengths that you observed. Questions? I will give you one, well, yeah, it's a, if you have visible light, and y'all, you may want to write this down because it's a checkpoint for you to make sure you're doing your calculations correctly. If you have visible light, Roy G. Biv, the wavelength will be 10 to the minus 7 meters. If you have visible light, the frequency will be 10 to the 14th per second. Yes. Wavelength is 10⁻⁷ meters. Frequency is 10⁻⁴ per second. And energy will be 10⁻⁹ joules. That, what I just gave you is true every time you're dealing with visible light. Meaning you have Roy G. Biv colors. Okay, so we just basically had to start a conversation related around waves. Now what we're going to get into is really why is an electron considered both to have a particle wave duality? Well, one of the observations that led us to say that it was a particle, meaning it was this dense mass object. You can think of it like a pebble, was the photoelectric effect. Now, for the longest time, classical physics basically assumed that, again, remember, intensity was related to the amplitude. They assumed that light rays just needed to have the right intensity, the right amplitude. And we could dislodge an electron from a piece of metal. But that's not what was observed. What we observed instead is that this incident light had to be the correct frequency of light. There was a threshold frequency. And we had to have something that was past that threshold in order for that electron to be ejected. Well, the only way we can think about this is if we're going, okay, so these have to be particles. And it's kind of like moving a boulder. You got to give it, you can't just hit it with a certain amount of energy and just keep hitting it with that energy and expect it to eventually move. No, you have to give it the right amount of energy to get it moving. So we started thinking about electrons as particles. And you have to give it just the right amount of energy, meaning you have to have just the right frequency or greater in order for it to overcome its binding energy and be ejected. So the photoelectric effect meant light had to be quantized. Light and electrons have to be particles. Here we get into this whole wave-particle duality. You had to have one photon hit the metal with the threshold frequency in order to eject the electron, in order to overcome the electron's binding energy to the metal. You may go, where is this ever used? And I would say, look up. That's what's going on in your light bulb. It's the photoelectric. We have to zap it with enough energy to eject an electron And those electrons are traveling from one end of the light bulb to the other end of the light bulb. And as they travel through that bulb, they provide light. Just like the hydrogen atom. We had to supply, well, we'll get to the hydrogen atom here in just a moment. But in order to do the photoelectric effect, we have to break that attraction between the electron and the nucleus. And you had to supply it with just the right amount of energy in order to break that attraction. So we can look at an example here. I know it's a nitrogen gas laser pulse with a wavelength of 337 nanometers, contains 3.83 millijoules of energy. How many photons does it actually contain? We can figure out the number of photons using this equation where the pulse energy divided by the energy of a photon is equal to the number of photons. Now, to get to that, we have to first figure out the energy of the photon. And we're going to figure out the energy of the photon using the equation that we used previously, which I gave you, which was E is equal to hc over lambda. H is 6.626 times 10 to the minus 34 joules seconds. Speed of light is 3 times 10 to the 8 meters per second. All of that is divided by wavelength, which has to be in meters. So therefore it's 3.37 times 10 to the minus 7 meters. And when you get through calculating this, you find that the energy of that photon of light is equal to 5.89 times 10 to the minus 19 joules. Now, in order for us to use this, we're going to have to make sure that the energy of the pulse and the energy of the photon are in the same unit. So you're going to have to convert that millijoules into joules with the fact that there's 1,000 millijoules in 1 joule. So therefore it's 0.00383 joules. So using this equation, the pulse is 0.00383 joules divided by 5.89 times 10 to the minus 19 joules. That is going to equal our number of photons. So therefore, we wind up with a number of photons of 6.50 times 10 to the 15 photons. And there is no unit. Because it's a counting number. Number of photons would be a counting number, so there would be no unit. So again, A nitrogen gas laser pulse has a wavelength of 337 nanometers and it contains 3.83 millijoules. So we knew the wavelength, we knew the energy of the pulse. How many photons does it contain? To get to the photons, we had to take the energy of the pulse and divide it by the energy of a photon. So we had to get the energy of a photon using the energy is equal to hc over lambda. In using energy equals hc over lambda, I made sure that my unit was in meters for my wavelength so that the unit matched. That gave me the energy associated with the photon. Then I took the energy of the pulse in joules divided by the energy of the photon in joules, and that gave me my number of photons. So in other words, we have a counting number again. So think of 1, 2, 3, 4 until you get to 6.5 times 10 to the 15th. That's how many photons was contained in that wavelength with that amount of energy. Okay, so yesterday you observed the emission spectrum of hydrogen. This is one of those cases where an electron behaves like a wave because we see light. We see part of the electromagnetic spectrum. When you shined that hydrogen lamp through a prism, you got 4 distinct lines. You got 2 purple lines, one of which I had to give you. You saw a teal line, which just shows up as blue, and you saw a red line. Each element has its own unique spectrum. One of the post-lab questions asks, how can you tell that this celestial body, I forgot the exact wording, but essentially, this celestial body is mainly made up of hydrogen? Well, we take and we concentrate that light that is given off by that celestial body, we shine it through a prism, and we're going to get 4 lines. We're going to get the 4 lines of the hydrogen emission spectrum. If it were any other element, we would see other lines. So hydrogen has, or helium, for example, it has 5 lines. Barium is much more complicated. This is neon down here where there's a ton of different lines. So each element has its own emission spectrum. So if we're looking at anything that contains hydrogen, we're going to only see those 4 lines. If it contains helium, we're going to see 5. They're different. Yes.
What determines that? Like, can that be changed with like isotopes and stuff like that?
It isn't going to get changed by isotopes because the isotope only differs by the number of neutrons. What determines all of this is literally the electron attraction and repulsions within the atom. Now, as I tried to describe yesterday, because I didn't have my printout or my pictures. If you look at emission spectra, you tend to have lines on a black background. When you look at an absorption spectra, it's just the reverse. Where the lines that were on the emission spectra are now void of color on the absorption spectrum. So they're just reverse of each other. So you asked what causes this. And I gave an example yesterday, but basically, when you excite an element, the electron is going to travel to some layer away from the nucleus. One is always the layer closest to the nucleus. It's going to travel to some layer away from the nucleus. When it relaxes, it gives off an electron of, when it relaxes, the electron gives off light of a lower energy level. Now, when you get into helium, you got 2 protons, 2 electrons. The protons are positive, but you got 2 electrons that they're attracted to the protons, but they also repel each other because they're both negatively charged. And things start getting a lot more complicated. And when you go to lithium, you now have 3 protons and 3 electrons. It gets even more complicated. So this is very simplified. This diagram is extremely simplified, but this is what's going on in the atom. For hydrogen, again, we took the electron in the 1, which is the electron closest to the nucleus. We excited that electron to some layer further out. As that electron relaxed to the second layer, it gave off light. So as it relaxed from 5 down to 2, it would have given off a purple light around 434, which most people couldn't see. The ones that were obvious was the one that relaxed from 4 down to 2, which gave off that teal blue green line at around 486. Most people had it around 480. And then the other one that was obvious was when it relaxed from 3 down to 2, it gave off the red light around 657. That series where it relaxes to n equals 2 is called the Balmer series. It's the series of radiation that gives off visible light. But you can get other types of radiation given off when the electron relaxes. You're not just exciting one electron at a time, you're exciting a whole bunch of atoms at a time. And some of them will relax down to 2, but some of those electrons will go all the way down to 1. If they go all the way down to 1, then you're going to get ultraviolet, the Lyman series, and you're going to have ultraviolet radiation. So if you see in the homework problems, ultraviolet radiation, that means that it relaxed all the way back to n is equal to 1. The other series I show here is the Paschen series. The Paschen series, the electron relaxes to n is equal to 3. In the Paschen series, if you see infrared, that means you're dealing with the Paschen series. So again, Lyman series, ultraviolet radiation, it falls to n is equal to 1. Balmer series, meaning you have visible light spectrum, means that the electron fell to n is equal to 2. And the Paschen series means that infrared radiation was given off, and it means the electron fell to 3. Or relaxed to 3. In the lab, you were to calculate the energy level for the relaxation on the hydrogen emission spectrum. To do so, you're going to use the Rydberg-Balmer equation. The Rydberg-Balmer equation is 1 over the wavelength, and this is the Rydberg constant. Now, when you do the homework on active, they give you the constant. Just make sure that the wavelength and the constant match. Again, it's all about matching those units. But anyhow, in this particular case, it's per nanometer, therefore the wavelength would have been in nanometers. That's multiplied by 1 over n sub f squared minus 1 over n sub I squared. If we're talking visible light, which is what you did yesterday, n sub f is 2 squared, so this is 1/4. And you have to calculate n sub I squared. I'm going to try to do that calculation so that you have something to work off of before we leave. I'm watching my time carefully. So let's look at hydrogen emits a line of infrared radiation with a wavelength of 1282 nanometers. If it's infrared radiation, what energy did the electron relax to? It relaxed to 3. It's the Paschen series. What energy level did the electron relax from? Well, that's where we're going to use 1 over the wavelength, 1282 nanometers, is equal to 1.097 times 10 to the minus 2 per nanometer times 1 over n sub f squared, in this case 3 squared, minus 1 over n sub I squared. The first thing I do is I'm going to simplify the fractions. So 1 divided by 1282 means it's 7.80 times 10 to the minus 4. That's equal to 1.097 times 10 to the minus 2 times 1 divided by 9 is 0.111 minus 1 over n sub I squared. The second thing I do is I divide by the 1.097 times 10 to the minus 2 on both sides. When I do so, I get, 7.8. .0711 is equal to 0.111 minus 1 over n sub I squared.
The next step that you're going to see me do is subtract the 0.111 from both sides. So I'm going to flip it to the next screen and rewrite this real quick. So I'm going to subtract out 0.111 from both sides. And you get a negative 0.0399 is equal to a negative 1 over n sub I squared. I then multiply by a negative 1, basically to turn everything positive. And then the next thing I do is I use the x to the minus 1 button on the calculator to take the inverse. When I do so, whoa,